Okay, maybe now it's time for start the course. And for chemical engineering, the some of the most important purpose is for the mixture separation, uh, especially for the homogeneous phase system separation, like liquid and liquid and gas and gas. For the liquid and liquid separation, we have different kind of technologies. Like last week, we used the distillation because of the boiling point is for the mixture is are different. So we can increase the temperature for the mixture. The light component can be turned into vapor, and from the top of the powder be separated, and the heavy part, heavy component, uh, at the bottom of the powder to be separated. And also there are other kind of the liquid separation technology, like the membrane separation. Because of the molecular particle size for different components is different. Uh, the small part can pass through the membrane, and the big part cannot pass. So the mixture can be separated. Also, there are like something like the crystallization, because the solubility of the mixture is different. With the temperature changes, the some component can turn into um, solid and be separated. Also, the membrane separation can be used for the gas and the gas separation. And another very important separation technology for the gas is the absorption. Is what we will learn today. How to control, how to uh, operate this absorption toner. So for this part, we also use this one to continue to software list and the 1547 for this part. Okay, 1547. Here actually we have several different kind of experiments. If you translate it into English, the first three is a guidance mode. The guidance mode for the dry um, packings, for the wet packings, and also for the mass transfer coefficient measuring experiment. The first three is a guidance mode. You can do that if you didn't do it before. The composite uh, experiment is a 4 and 5. So today's course is a 4 and 5, 4 and 5. Okay, 4 and 5. Actually, the 1, 2, 3 is same for the 4 and 5, but the 4 and 5 experiment can generate a report. Okay, but and the first three experiment cannot generate a proper report. So the composite experiment for you to do is a 4 and 5. It's for the four the fourth experiment is maybe the hydrodynamics performance for the absorption tower measuring, and the fifth experiment is for the carbon dioxide absorption experiment. So we will do the first one is the hydrodynamics performance for the uh, absorption tower. Firstly, so please remember the fourth and fifth experiment. You will have to do that. So because the mixture is separated because of the solubility, so we choose to do the fourth part. Yeah, 4 and 5. The fourth and fifth. Okay, the fourth and fifth part should be finished. Have to be finished for absorption. So first we turn a language into English, and then you may choose play. Here is some type of the packings. Is a bar ring structured or racine ring. You can choose random one. However, here is we use the first one to as an example. To start an experiment, it contains one tauler, which is actually distillation absorption. So what about the first? The second, and third part for the absorption experiment is a guidance mode. Okay, it's easier to be operate. However, it's the same to the fourth and the fifth one. So if you have time, you may, if you feel the experiment is hard, you may just follow the steps one, two, three, and then four and five. But if you feel that's okay, that's simple, you may just start from the fifth one, fifth and fourth one and fifth one. Okay, so this experiment contains one tower, is an absorption tower, is a desorption tower actually. So I if it is a chemistry experiment, if we try to find the solubility of mixtures, of gas mixtures, we may use a conic flask to make sure the temperature and the pressure in the flask to be stable, and we feed the gas mixture into it. And also there are some absorbent in the. I'm sorry, maybe someone didn't close his microphone because I can hear you somehow. Sorry. Uh, okay, if it is a chemistry experiment, if we want to find the solubility for some gas, we will use a conic flask to contain uh, liquid or absorbent, and feed the gas mixture into it to control the temperature and the pressure in the flask to be stable. In that case, if it is enough time, maybe 20 or 30 minutes later, we will try to measure the solubility of the gas mixture. But it is a chemical experiment because of the device is it has limited space, and also for the operation, for the absorption uh, operation is the time consumption is limited. So not all the ideal like for in this case, not all the ideal carbon dioxide component can be absorbed in the to the absorbent or for the water in the water. So we have to find what is the uh, how we determine the mass transfer coefficient for this device, because the absorption is kind of a mass transfer for mass transfer from the gas to the liquid, the carbon dioxide mass transfer from the gas to the liquid. Okay, but not all the carbon dioxide can be absorbent, even not the ideal or equilibrium part, carbon dioxide part, can be transferred from the gas to the liquid. Only some part of the carbon dioxide can be transferred. So in that case, we have to find what is the mass transfer coefficient for the device, and how we define the mass transfer coefficient for the device is something we have to calculate it. And before that, for every kind of chemical device, it must have some appropriate operation condition. Like the for this case, the gas will moves from the bottom to the top, and the liquid will moves from the top to the bottom. And because it is it will create a counter current mass transfer process. then the water moves from the top to the bottom, and then the gas moves from the bottom to the to the top, counter current mass transfer to each other. But if we increase the gas flow rate, as we can imagine, maybe the liquid cannot move from the bottom from top to the bottom. It can hold in the tower, and even can move from the bottom to the top because of the gas flow rate is too big. So in that case, we have to find the uh, hydrodynamics of the tower to find appropriate uh, operation condition or operation range for this part. What is the appropriate uh, gas node and also the appropriate liquid node? Uh, because of the liquid node and the gas node is different, the pressure differences or pressure loss for this tower is different. So we will find first to find if the liquid node is zero, we will try to increase the gas flow rate from zero to maximum to find a pressure differences, and then we will choose a a constant or a designed liquid load, and to find it at that time what is the pressure change uh, with the versus the gas flow rate from zero to maximum. And for each different kind of liquid load, there will be different curves will be will be generated via this way. So maybe from the introduction, it's easier to say. Yeah, like for this one, the pressure drop of the packings, if the node, this one L0 is for the liquid node is zero for no liquid, and for the L3, L2, and L1 is the liquid node is bigger and bigger. Here U for the x-axis is for the uh, gas flow rate. As the flow rate increases, the pressure drop. Here, the y-axis is actually the pressure drop of the of the tower, or maybe the uh, delta P divided by Z. Z here means the height of the pressure tower. So, and we increase the um, flow rate of the gas, the pressure drop of the tower will increase. Okay, if the no liquid, if it is no liquid, the pressure drop and the flow rate of the gas will have a linear relationship. Okay, and if it has some liquid or some liquid load is not zero, the first the pressure drop and the flow rate of the gas will firstly become a linear relationship, but in some point the pressure drop will increase a lot rapidly, and in some other point they will increase the even faster. So so these 2 points are very important for the absorption tower operation conditions. So these 2 points are very important, and we change the liquid node from L1 to L2 to find in another 2 points, and also we can increase the liquid node from L2 to L3 to find uh, even more two nodes points. So so in this point, so in this part, in this zone, we may find its appropriate operation condition for the absorption tower operation. The first point we can call it is a loading point, and the another one, a this point we call it the flooding point. Okay, so loading point, flooding point, uh, between them are the appropriate operation condition for the absorption tower. So I just read them. The pressure drop is an important parameter in the tower design, and the energy consumption for the tower is determined by the velocity of the gas which passes through the packings. The pressure drop is controlled by the gas and liquid flow rates. the relationship between the pressure drop of the packings and the gas velocity on the different amount of liquid spray or different liquid load is shown in Figure 1.1. Okay, when the amount of liquid spray is zero or L zero, there is a linear relationship between delta P divided by Z. Z here is the height of the packings or height, or the okay, you can simply consider it as the uh, Tauler height of the dry packings. Because of the at this time there's no liquid spray, so we can call it the dry packings. Dry packing. So the pressure here we can call it the dry packing pressure. And the straight line zero shown in the figure. Okay, so for this curve, this is a dry packing pressure curve. And when there is a certain amount of the spray, the relationship between the delta P divided by Z or unit uh, delta P becomes a broken line relationship. There are two turning points. Okay, two turning points. The first one we call it the loading point, and another one we call it the flooding point. Okay, the first one is, and the relationship is divided into three sections. Okay, the constant liquid holding area, the carrier area, and the flooding area. So this area is the constant liquid holding area, and this area is a carrier area, and this area is we call it a flooding area. The appropriate operation condition for the absorption tower is the carrier area. Okay, we want to make sure the liquid node and gas node between these 2 points is appropriate, is acceptable for this for the operation for the absorption tower. So for this case, we have to do the experiment for the hydrodynamics experiment, performance experiment, firstly, before we really do the absorption experiment for this toner. So how we do that? We simply follow the steps in the score. Um, First is determination of the relationship of the main toner and dry toner data processing, and for the determination of the curve for the desorption toner wet is actually the wet toner data processing. Okay, so it contains into four parts. The last thinking question is something you have to answer in the reports or in the experiment later. So we just follow the steps one by one. First one is determine the is actually for the because at this time there's a no liquid loading, so it's a dry pressure experiment, measuring experiment. So so this is a desorption tower or the tower itself, and this is a rotometer for the air, and this is for the rotometer for the liquid, and the liquid will moves into a downward way, and the gas will moves into upward way. Okay, so we just follow the steps. Turn on the main powder, and then we will find. Try to read. There's something in this panel. As you may find, there are some like the temperature of the top and the bottom of the uh, tower for the liquid and also for the gas. They are all 25 Celsius degree. The temperature here is very important because the for the calibration of the velocity or the calibration for the volume flow rate for different, uh, especially for the gas, is very important, and it is what we well understand in for this case for this experiment. So you have to make sure the temperature uh, and read the temperature case by case. If it is a real experiment, I mean, if it is a in on-site experiment, the temperature will change because the room temperature is changes. However, it's the virtual simulation experiment, maybe the temperature is constant into the 25. But you have to make sure if it is a real experiment, it is an on-site experiment, you have to read the temperature case by case. Okay. So then fully open the bypass control for the valve. Because this is a Vortex air pump. This is the Vortex air pump. We use it to suck the air from the atmosphere. There are three kinds of way to control the or to change the flow rate for some fluid transportation device. Something like the centrifugal pump or the vortex air pump. There are three kinds of way to change the flow rate. First way is to change the opening of the pump of the valve after the pump or after the fan. Okay, the first way. The second way is directly change the frequency of the pump. That is change the rotation speed of the pump. The third way is the bypass control, because the fluid will moves into the system or moves into the bypass. Okay, if we change the bypass opening, the fluid into the system will be changed. That means if we increase the opening for the bypass, the the fluid into the system will decrease. If we decrease the bypass for the atmosphere, the fluid into the system will increase. Okay, so that's and for the vortex air pump operation, the opening of the after the pump have to be opened before we start up the pump. But for the if it is a centrifugal pump, the alternative of the pump, if there is a valve, it has to be closed before we start up the pump. Okay, centrifugal pump. So that's the differences between the centrifugal pump operation and the vortex air pump operation. So for this case, we have to fully open the air bypass control valve to make sure the uh, alternate of the pump fully opened before we start up the pump. So fully open it. Okay, then we will start the fan or start the pump. It's a desorption fan, but actually it's a vortex air pump. Okay, so we find. Okay, I think it's. I'm sorry, this one. This one. If you turn on the power button for the fan, there will be some noise. Okay, it's hard to control it. Okay, and then fully open the regulation valve for the airflow rate for the desorption tower. It's actually open the valve for the system. Okay, okay. Now, in this case, the valve for the system and valve for the atmosphere are both fully opened. If we try to increase the flow rate for the to the system, we can decrease the opening of the to the atmosphere de- or the decrease the opening for the bypass. Okay, so gradually turn down the air bypass control valve and record the height differences of the U tube under each airflow of 10 groups. Here we use this rotational meter to read the flow rate for the air, and we use the YouTube pressure meter to read the pressure differences into the tower. So the YouTube uh, pressure meter contains two uh, water column or liquid column. It contains water or it can contain other kind of liquid like the mercury. So we can calculate the pressure differences by the delta P equal to rho GH. Okay, rho GH. raw material G and H for the height differences of the YouTube, which I think you already learned in the theory part of this course. So now we simply close it a little to find if the if the if the meter, okay, YouTube meter changes or not. As you may see here, the display value for the YouTube is 0.07 centimeter HTO. Okay, so the liquid contains in the YouTube meter is water actually. So and also for the airflow rate, here is 4 n cube meter per hour. So what is the n here means? Is someone know that? What is n here mean? Why is n cube meter per hour? Because normally it's just a meter, cube meter per hour, right? So why is n here? What's the meaning for the n here? So actually n here means normal. Okay, normal. And it means it's for the normal condition for the meter. For each kind of meter, it has um, a constant measuring environment. Okay, so normal condition for this meter, that means is for 20 Celsius degree and 1 atmosphere. Okay, if the temperature or the atmosphere or the pressure changes, maybe the uh, not maybe the flow rate read on the meter can be changes. So we have to uh, do some calculation to calibration the reading. So this meter, this rotational meter is actually for the air and 20 Celsius degree and 1 atmosphere. So because PV equal to nRT. If the atmosphere, if the pressure changes, if the temperature changes, the reading uh, have to be calibrated uh, before use. Okay, so the reading is something. It's not a real it's not a real volume flow rate. We have to calibrate it. Okay, because the PV equal to nRT. So in that case, we may use this is the first set of data. The pressure differences is 0.07 and the flow rate here is a 4.00. Okay, but this is a normal condition. In normal condition, we have to calibrate the flow rate. Okay, so how we calibrate it? We may use Excel 2. Okay, here I already sent this Excel to you for convenience. So as you may find, the this is a equation for the calibration. Okay, V real equal to V measured and times the rho measured divided by rho real. Okay, and here is some 0.5 exponential. Because of PV equal to nRT, so P equal to rho RT divided by M. So the as you may see, the time the temperature differences and the uh, density differences is changes controversially. Okay, so because the temperature here in in this experiment is 25, if you remember, is 25 for this experiment. But the standard the uh, condition for the meter is 20 Celsius degree. So we have to change the reading from the real from the measured into real. Okay. So the density differences, coefficient here is 0. 98. So the first reading for the reading one is how much? Is 4. Okay, is 4. First one is 4. And we can use this calibration. So the real uh, flow rate for the meter for the gas is this part. You simply copy it into the data record. Uh, Here, water flow rate is 0 because it is 0 loading, right? And the air flow rate is this part. And the air velocity because the diameter of the tower is something we know, and we simply calculate the uh, uh, flow area for the tower and can calculate the velocity for the gas. And the height differences in YouTube, and we read from the from here. I'm sorry, is 0.07. It's something we can copy it 0.07, and then we have to transfer the unit into centimeter HTO into Pascal. Okay, 0.07, and because it's is equal to rho gh. Okay, rho gh. Here rho, even the rho we give it. Gravity is 9.8, and we copy the result from Excel. And then finally is a delta P divided by Z. Z here is a packing layer height. Okay, packing here height. The pressure, we use this value divided by 0.78. We can get the result. Okay, this is the first group of data. And then because at this point there's only fluid in there are only gas in this tower, and there's no mass transfer. So uh, if you remember that there are three kinds of transfer in the chemical world: is a mass transfer and temperature transfer, and also the momentum transfer. The momentum transfer is most easily to be obtained to be stable. So there's no need for many stable time for this operation. So we simply decrease the opening for the bypass and find the and in that case increase the flow rate in the system. And here we record. We record to find the first one is 7, and also the flow rate is 0, and maybe we have to file match. Okay, and the air flow rate here is 7.6, 7.6, and the air flow rate is something, and the height here is 0.18, 0.18. Okay. So for this part, I'll do a full set of data, and but for you, you have to do uh, at least 10 sets of data. Okay. So continue decrease the opening for the uh, bypass, and next one is 17.20. So the real one is I'm sorry. The height for YouTube reading is 0.56, and then as for the pressure drop, we change it 0.56, and we change it into Pascal, and to find the delta P divided by Z here in this one. And the last one, we continue decrease it. Maybe this one, maybe this is enough. Okay. And for this part is the standard flow rate for the air is 35.6, 35.6, and so the real one should be under low zero, under zero uh, liquid loading, and air velocity here is 2.22, and the pressure differences is 1.52, 1.52, and the toner difference is 1.52 at this part, and then is this one. Okay, so in this case I submitted. Uh, so for the score part, I have to do at least the 10 set of data to make sure uh, all the data is accepted by the experiment. However, now I only did four. Okay, four parts. So for the dry toner data processing, I think that is finished. Then we will do the wet pressure experiment. So in that case, to control the water flow rate at some flow rate, that for in this case is 100 liter per hour. Okay, so for this fully open the bypass, follow the steps. Fully open air bypass control. Fully open it. That means from zero, from the system, then from zero to maximum. Okay, to make sure, and then start the desorption water pump because I didn't open it in appropriate sequence, so it didn't give me the system didn't give me a full score. However, I think you can do that. Good, and start the water pump. Okay, and this time we can control the uh, as you, if you remember, I said there are three kinds of way to control the flow rate for the liquid, and for this case, it's only use the first one. First method is the control the opening for the uh, valve at the end of the pump. Okay, so we may use this one to control. Here is first control it at 100 uh, liter per hour. Okay, and then we read it here. I think it's 25. Yeah. Okay, 100. Almost 100. Okay, and then grad. What is mean not in sequence? Because if you remember, if you have watched the video, uh, I wrongly opened this pump before I opened this pump. Okay, and earlier for this experiment. Okay, see, thank you. Then control the water volume at 100 liter per hour and click File Management in the function menu to select the corresponding file. Okay, I think it's asked us to here to this one. Okay, for this one, wet packing water, to change it into wetter packing water, and then redo the experiment again. Uh, Increase the velocity in the system for the air from minimum to maximum. Okay, so I think it's close this one first. Maybe that's okay. Okay, so at this stage, the first set of data is 4.8. So maybe here, for maybe this one, I make it empty. Oh, can't. Okay. So for the wet part, for the wet pressure, the first set of data is a 4.8. 4.8. And the velocity here is similar. Data recording. Okay. Water flow rate here actually is read from here is 100. Okay, 100. And then is air flow rate. Its standard is 4.8, and the real one should be 4.75. And the air flow rate, air velocity is similar calculation process. As you may find, the height differences or the pressure drop is increased or not, because from the zero you can find uh, when it's close to 4 uh, cubic meter per hour for the dry experiment, the pressure drop is about 0.07 centimeter for HTO. But now we find it's 0.14. Okay, it's two it's increased or not actually. So the first one is 0.14. The total pressure is one is this part, and also for the this one. And then we continue decrease the bypass, and yeah, maybe at this stage there is mass transfer between air and water, uh, because there's a air from bottom to top, and the water moves downward. However, at this stage there is no mass transfer between them, and we will not need to wait too long time to make sure the system is stable. So just when you control the flow rate at some stage, simply click record it. No need to wait too much time. Okay, because there's no mass transfer in this case. 100, and second one is 8.8. 8.8. 8.8. So the real one should be air velocity is, and height differences is 0.37. 0.37. And also for the last one, for the pressure differences. And then we continue. Okay, close it. Maybe this one is enough. 100, no change. And for the 18.8, 18.8, copy the next one. Flow rate should be, height differences is 1.33, 1.33, 1.33. Okay. So after that, you may continue to decrease the opening for the bypass and find the other sets of data reading. But from at this stage, if you remember from the introduction part theory, uh, the curve for the dry pressure is a linear relationship between the delta p for the velocity of the gas. But for if there is a liquid loading, there are two turning points, right? Turning points is a loading point and flooding point. So how we determine when is a loading point and when is a flooding point is actually, if it is a real experiment, we will find from the phenomena. Okay, we will observe the phenomena. And this stage you can find the yeah, from the phenomena, from the animation. Uh, in some case, there should be water moves hold into the packings. Okay, not move, holding. In that case, it is a loading part, is a loading point create. And from the observation, if the liquid moves from bottom to uh, top, and even at the top of the tower and the top of the packings, the fluid jumps. Okay, the jumps or boiling, something like the boilings, and that stage, it's a flooding point. Okay, it's a flooding point. The fluid moves upward, and at the top of the packings, the fluid boilings, uh, not boilings, something like the yeah, not boiling, yeah, boilings in and at the top of the packings. However, it is a because it is virtual simulation experiment. The animation may be not that good, so you cannot observe the phenomena for for liquid moves in different way, and also you can find the determine when is a loading point and the flooding point for this experiment. So how we determine when is the flooding and when is the loading point for this case? The only thing we can do is to find for the pressure differences. Okay, pressure differences. As you remember, the at the beginning, the pressure differences and the velocity is a linear relationship, and after some point, it will not into the linear relationship. Okay, so at that stage, you can determine this point is the loading point. And another point you can determine that is a flooding point. Okay, so I have to make it clear that in the on-site experiment, the 2 points are determined by observation the phenomena. Okay, but because this is a virtual simulation experiment, you have to determine the 2 points because of the relationship between the pressure drop and the velocity. Okay, so it's harder. I think it's even harder for you to determine these 2 points, but you have to try that. Okay, so uh, so for this experiment, you have to determine when is loading and when is flooding. Okay, even you cannot find the phenomena from the animation. Okay, so next point is about this part. I'm not sure it is in uh, it is now at the career area or flooding area or still liquid holding area. I'm not sure, but you have to make sure. Okay, you have to find it by yourself by analyze the data. Okay, and this time the flow rate for air is 31.99. 31.99. Okay. Also 100, 31.99, 31.99. And the flow rate here is 1, and the height is 3.23. 2.23. Also 3.23 delta. Okay. In this case, I can submit it. So for you, you will have to do at least 10 sets of data, and I think you may do more than 10 sets of data because you have to find the loading point and the flooding point by analyze the data, analyze the relationship between the pressure drop and the air velocity. So you maybe you have to do more set of data. Okay. Uh, After that, I think it's finished for the fifth experiment for the opening for the operation part. So now we may check from the diagram. Uh, the dry field, say those, but why it's only observe the curve for the dry? I think. Eh? Oh, this tuber. So you may choose the appropriate uh, file. Default for me, I choose the default file because I for the file management here part, I didn't save the data for the drive filter. I only save the data for the default file filter, drive filter. I think it's wrong. Maybe it's wrong. Okay, wrong English spelling. Uh, So you may choose your file to, or you can may even create more file like water packing water equal to maybe 300 liter per hour. You can even create more and to generate appropriate files. So at this stage, you may find there are only say data recording. Why it's still linear? Okay, maybe I have to increase the gas flow rate even bigger to make sure the. Uh, I think something. Okay, yeah. Maybe I did more set of data. The curve, the slope of the curve will changes. Okay, will change. If it only has four data, the slope seems like a still a linear relationship for this part. So, but for you, you have to find the loading point and the flooding point. Okay, then we do the next procedure for the experiment. Is something like the end of the experiment, and at the end of the experiment, fully open the air bypass, fully open the bypass. Okay, to make sure the flow rate in the system is minimum, and then close the regulation valve of the meter. Okay, close this, and then turn off the fan. Okay, or the vortex air pump, and then close the bypass valve. Close it. So you have to remember the operation procedure or operation steps for uh, air pump and the centrifugal pump is different. Okay, the alternate valve, the opening is different. The procedure is different. And then close the regulation valve for the water. Close it, and then close this fan, I think. Close this pump, and then turn off the main powder. Okay, turn off the main powder. It's hard to. Okay, then finish the experiment, and after that you have to answer some questions in the analysis part, or maybe I think these questions are the same for the fact for the. I'm not sure. Okay, answer the questions for this part, and then generate a report to find the experiment here. As I said, you have to draw the flow rate by hand by yourself. Okay, so first this figure you have to draw by hand by yourself, and then you have to create. Oh, maybe I didn't create enough curves for this part, because there should be at least two lines, right? One is for the dry pressure, one is for the wet pressure, or liquid loading equal to 100. So you have to uh, add something in this figure, or you may increase, or you may generate this figure by yourself. And then for the calculation, and also for the result discussion. Okay, for this part, the calculation is quite easy. It only contains the dry pressure calculation and also the wet pressure calculations. So this part is easy. And after that, for the fifth experiment, you have to combine. After you finish the fifth experiment, you have to combine fifth and fourth experiment report together to generate a complete report. So now let's do the fifth experiment. So quit and this part. Okay, quit and this part, and to do the next one for the fifth one is for the carbon dioxide absorption desorption experiment. So for this experiment, you may read from this from the behind. There are some actually it's a guidance book. Okay, for the construction for the experiment. The second one, the second one is for the carbon dioxide English version. Okay, so you may follow the steps and follow the calculation procedures in this file. Okay, the second file. You may see here are some purpose, something for the theory, and the most important thing is for the calculations actually. Okay, you may find the calculations here, the details for the calculations. Okay, and for this part is actually for the calculation for the hydrodynamics performance measurement of the packed powder one. Okay, so for his part, for his example, the flow rate is a 7.5. However, he didn't change the flow rate from the measured into a real one. As I said, because the temperature is different, because the temperature in the atmosphere is 25 Celsius degree, but for the standard meter is for the 20 Celsius degree. So we have to calibrate the flow rate from 20 into 25. So so here the 4.5 is not correct. So if you copy the flow rate directly from the meter, I will give you a wrong. Okay. So this is for the gas, for the hydrodynamics calculations. As you may see here this is his calculation example. And then is for the absorption and desorption of carbon dioxide. As you may see, here are many. Okay, but I think the right thing is you may just follow it. That's okay. You just follow the steps here. So how do you calculate everything? Till now, I will give you how to do the experiment and how to write the report. You may just follow the guidance book. Okay. Okay. Now we have two tolerers, absorption tolerant and a desorption tolerant. The way is here is a carbon dioxide cylinder, and here we have a fan, another fan, absorption fan. And here we have a desorption fan is actually vortex air fan pump. And we have two tanks, absorbent tank and a desorptant tank, desorption liquid tank. Okay. The mixture can be created by uh, using the carbon dioxide from this cylinder and also suck the air from the atmosphere and control the flow rate for carbon dioxide and also the air and make sure the carbon dioxide into some constant concentration and then create the mixture to feed the mixture into the absorption tower from the bottom and the mixture will move upward and to the top of the tower and it emitted into the atmosphere. However, in the aperture, I mean in the on-site aperture, the emitted gas will be absorbed. Okay, and the liquid or absorbent liquid actually it's air, actually it's water, will moves from the tank by a pump and from the top downward into the desorption tank. So the air, the gas and the liquid counter current mass transfer with each other. After the mass transfer, the liquid will have some constant carbon dioxide component and moves into the desorption tank. And of so from the top there will be from okay first from the bottom there will be a mixtured gas with constant concentration of the carbon dioxide because we can control the flow rate of both okay carbon dioxide and air and also there will be a liquid after the absorption process. The concentration of the carbon dioxide in the liquid we cannot know. However, we can measure them later. Okay. From the top of the absorption tower, there will be a pure water. Okay, pure water. So the carbon dioxide in the liquid is zero, and also will have a exhausted uh, gas contains some component, some concentrations of carbon dioxide. The concentration of the carbon dioxide we also don't know. However, we can calculate later by by how to calculate by mass material balance equation. Okay, mass material balance equation. So that's basically the how we do the experiment, the theory, and the water in and the water after the absorption, it will moves into the desorption tank. And in this experiment, we will use air to desorpt the carbon dioxide in the liquid, okay, to make sure that the the exhausted liquid contains no carbon dioxide, neither. Okay, so actually this fat is used for the desorption because we have to absorb the carbon dioxide from the liquid. Okay, later in the second step. So we simply follow steps here. It asks us the experiment on determination of absorption mass transfer coefficient, and then is for the dry tunnel data procession and some thinking questions end of the experiment. The second experiment actually we only have one set of data because but it contains mass transfer, so we have to wait uh, enough time. So in this case, if you read the uh, score part, uh, you may find there are about 20 minutes for the mass transfer stable to be stable. Okay, so we just follow the steps one by one. Turn on the powder. Turn on the powder and find or read all the values on the panel. Okay, actually, it's all about temperature. Okay, if you read, it's all 25 Celsius degree, but in the real atmosphere, it cannot be constant to be 25 Celsius degree. And then start up the absorption water pump. Okay, then we start up the absorption. I think it's this pump. Okay, start this pump. Okay, actually it's for the pump behind the behind for the behind the screen. Okay, and then open the regulation valve for the absorption tower flow meter. Okay, is actually I think is for this one. So how much we control it? Oh, just to 100. Okay, to 100 liter per hour. And we have to file management into the function menu to select the corresponding. Yeah, this one, 100. Okay, liter water flow. Okay, and okay, so in this case, the water moves, and the water will moves from top to the bottom to into the absorption tower. But why it's not? Okay, okay. Yeah, as you may see, the water moves from downward. Okay, water moves downward, and then yeah, I think I will already just start the desorption water pump because the water moves from this tank into the desorption tank, and we have to uh, uh, make sure the water liquid in a desorption tank back to the absorption tank. Okay, and open this one and control this valve. Not this valve. This control this valve into 100 into 100 also to be 100. Okay, so simply the tag the liquid in this tag moves from this tower and into the desorption tag and well moves into the desorption tower and back to the absorption tower. So the liquid flow rate should be equal to each other to make sure the uh, uh, level meter to be equal to each other. Okay. So at this stage we can add some gas into the system. Okay. Open the needle valve on the top of the carbon dioxide cylinder. So for the gas cylinder operation, there are two kinds of valve here. First is a needle valve, and then is a vacuum valve actually, and we read this one. Read this meter to find how much or what's the pressure we used to transportation for the gas. And this valve is open is for the this meter is for the cylinder itself. Okay, and you may say the 1.43 meter nanometer million Pascal is too big. Okay, so we can open this one to control the transportation pressure for the carbon dioxide. How much should we control? It's about 0.3 standard cubic meter per hour. Okay, so we read it from here. Maybe we still open this one. Yeah, it's 0.3. Okay, so at this stage, uh, the transportation driving force is about 0.3 million Pascal, and then we control the open the oh okay open the regulation. No, I'm sorry, I make it wrong earlier. So this one is only for 0.3 million Pascal. Okay, and if we want to control the flow rate for the carbon dioxide, we have to use the valve. Okay, use this valve. Okay, use this valve to switch it to be make sure the flow rate to be 0.3. Still not. Oh, too much. Okay, 0.3, and then to start the absorption fan. To start the absorption fan is actually this fan. Is actually this fan to suck the air from the atmosphere. So absorption fan is this one. Okay, open it and uh, control the air flow rate into 0.7. So from this meter, rotational meter, we control it to 0.7. Okay, 0.7. So at this stage, the mixture contains uh, zero point 0.3 liter per hour carbon dioxide and also 0.7 0.71 liter per cubic meter per hour air. However, all of them are in standard condition. We have to calibrate the flow rate later in the calculation part. So then is for the desorption. Okay, for the desorption. Desorption, we simply could open this one. I'm sorry. We because this is a atmosphere. This is a uh, vortex air pump. So we have to open the bypass valve firstly. Okay, open it firstly and start the fan, and then fully open the regulation valve. Okay, fully open it. So, and after that, we decrease this valve to uh, control the flow rate in the system for the desorption air. So how much is 10? Okay, 10. So this cannot be the control. Okay, it's about 10 kilometer per hour, and then we will uh, keep the system to be stable to about 20 minutes. Now the mass transfer is already proceed. The air and the mass and the liquid moves in a counter current way to mass transfer with each other in the absorption tower, and then we'll just keep about 20 minutes to be stable. Here we start, and here's a timer. You may read from the timer about the time, how much it costs, 20 minutes. So, however, now because it's only for the sample examination, not examine, it's only for the exam. So we will not wait for 20 minutes. Just wait here. That's okay. So let me see. The bottom gas concentration, the carbon dioxide concentration, we can calculate it by the flow rate, and the top liquid concentration is zero, right? It's pure water, and the bottom liquid concentration, we can use some um, acid base titration experiment to find the carbon, how much carbon dioxide in the liquid, in the bottom liquid. So, so we will use actually a HCl titration analysis. So uh, if you find the data record here, it contains some value you may use for the calculation for the titration, like the carbon dioxide density and the 20th degree, and also for the air density and the HCl concentration, because it's acid-based titration experiment. So you have to use some concentration for the acid and also for the base. For the BaOH2 concentration, and also for the how much BaOH2 we used for the for the V, okay, sampling is 10 microliter, okay. And also because for this for the carbon dioxide absorption, I didn't tell you earlier. However, you I think you already know that, because for the carbon dioxide absorption, it follows the Henry's law. Okay, follows Henry's law. If it is ammonia absorption, it follows other other law. Okay, so for the carbon dioxide uh, concentrate absorption follows Henry's law. So we use Henry's law to do the calculations. So here, after you finish the experiment, after 20 minutes passed, you simply click the sampling, and about 20, okay, 20 20 microliter sample are obtained from the absorption kettle and the desorption kettle. And also we can use the HCl titration analysis and to find how much for the samples. Okay, how much HCl consumption, okay, consumed for the sample absorption for the titration. Okay, so what's this value used for? It's for the actually you may follow the steps for the guidance. Okay, first, for the calculation for the experimental data of the absorption and desorption of carbon dioxide, the uh, air is at 0.7 liter standard cubic meter per hour, but it's for the 25 Celsius degree. We have to change it into 20th Celsius degree. So you use some calibration. Okay. After that, you will get a real air flow rate. Okay, real air flow rate, and also for the air flow is in the molecular per hour. So so actually it's for the here data recording, yeah, recorded. The inlet temperature, air flow rate, some blah blah blah. All this part, all this part, how to calculate them, you may follow from this guidance book. On the guidance book, it's for the air and also for the carbon dioxide calculation or the calibration, correction. Anyway, you may find a proper, the real flow rate for the gas and also for the carbon dioxide, or for the air and for the carbon dioxide. And then you will find the Y1 and a smaller, smaller Y1. Okay. Upper Y1 and the smaller Y1. One here, this subscribe means the bottom. If it is two, it means the top. Okay. So here is inlet carbon dioxide molecular rate ratio. A big Y1 is this part, and the smaller Y1 in this part, because it is followed the Henry's law. So the uh, absorption, I'm sorry. So the equilibrium concentration for the uh, X1 should be this part. So the concentration for in the liquid, the limitation for the liquid concentration in the bottom should be this part. Okay, should be this part, and the limitation for the uh, carbon dioxide concentration from the top should be this value. Okay, this is the ideal one. Ideal one, if it is followed the Henry's law. But the real one, how we calculate it is from the acid-base titration experiment. We use some HCl to be consumed for the titration. So how much we used for the calibration is here. Use this formula. 2 times concentration for the BaOH2 is actually this part is this one, okay, 0.1, and then times the V BaOH2 is a sample consumption for the BaOH2. This one 10, right, 10. But you have to notice the unit of the sample, okay, microliter, okay. And then is for the concentration and for the HCl and the sample, how much HCl consumed for the titration. And the C for the constant concentration for the HCl is 0.1, and the consumption for the consumed HCl is this part. Okay, this part. Okay, for the desorption total is actually for the bottom. Okay, desorption total is for the bottom. For the absorption total is for the top. Okay, because the liquid moves from the absorption total for the absorption tag and to the absorption total and to the desorption tag. So the liquid at the bottom is equal to the concentration of the carbon dioxide of the bottom of the absorption total is equal to the component sample in the desorption tag. So it should be this one. It should be 19.87 in this part. So V HCl1 should be 19.8. Okay. In that case, you can calculate the Ca2 and also the Ca1. Okay. And then you may follow this formula to find X1, X2 and X1. X2 and X1 is actually the mass concentration of the carbon dioxide in the liquid. Okay, in the liquid. So then you this formula is the uh, material balance equation to calculate the y big y upper y2 and the smaller y2 from the top of the total, because the subscribe 2 means top, 1 means bottom. Okay, so in this case the real carbon dioxide in the in the exhausted gas can be found, okay. And then because it follows the Henry's law, the equilibrium concentration can be found. The differences between the real uh, C and the equilibrium C concentration is a driving force. So the average driving force for the nuclear phase can be calculated for this case, for this formula. And after that, you can calculate two very important parameters for the absorption experiment. Is the number of the mass transfer unit and also the height of the mass transfer unit. Actually, these two, or we can call it NTU and HTU. And NTU HTU is not only for the absorption experiment, is also for the desorption. Is also for the distillation experiment. You may use this way to calculation, and then you can find or you can calculate the mass transfer coefficient of the liquid phase. Okay, so the K, big K, upper K, okay, how much it is, and then finally you will get the absorptivity. Okay, is how much of a carbon dioxide can be absorbed in this tower. Okay, so after you do the calculation, you may fill all the blacks in this table. Okay. After that, you submit it, and then uh, submit the generate the report. Here also we have a diagram. If we have a if we finish the experiment, you will have this diagram. Okay, and then we just stop here, and for the report, if you finish the experiment, you simply combine the fifth report and the fourth report together to generate a one report. Okay, to generate one report. There are two kinds of calculations. First is for the hydrodynamics performance calculations, and also for the mass transfer coefficient calculations. Okay, but both you may find examples from this from the guidance here. The guidance is at the bottom of the um, main page of this experiment. Is here. Okay, is actually here. Uh, the second one is for the carbon dioxide absorption and desorption experiment for the English version. Okay, you may find that here are some other uh, video. It's easy. It's for your convenience to do experiment. And then we assume that we already finished the experiment, and we will do the next stage. Okay, we will do the next stage is end of the experiment. Close the valve on the close the needle valve. Okay, close it, and close the pressure regulation valve storage button. Okay, close the water, air first, carbon dioxide first, and turn off the carbon dioxide flow rate regulation valve. Okay, rotational meter, turn off it, and then I think it's for the gas, air. Turn off the fan, turn off the absorption fan. and then turn off this meter. Okay, and fully open the this option. Okay, and then because it's the vortex air pump, so we have to fully open it and then close this one. Eh? Fully open the air bypass regulation valve and close the. Oh, I didn't to close this one. I'm sorry. So I have to close it earlier. Now I think because I didn't do it correctly, so maybe it still give me a full score. Okay, turn off the this option bypass, and then turn off the absorption water regulation. Okay, turn off this one, and then turn off the pump for the absorption part, and then I think for the this option pump. Okay, turn off this pump, this valve, and also for this pump, and turn off the powder. Okay. After that, data processing. Okay, data processing because I didn't do this part. So if you did that, I think you will get a full score. And thinking questions. Let me see the questions are easy, are same or not the same for the previous this experiment. Yeah, it's not same. So you have to answer both the 4 and 5 experiments. You have to find answer both questions. Okay. So after that report, to generate a report, and as I said earlier, to combine both reports together to create a new report um, for the absorption experiment. Then quit. So finally, okay, I think it's all for today's experiment teaching. So do you have questions? So I I want to say it again. So for this experiment, we have to do the fourth and fifth experiment together to combine one experiment and also to combine one report. Okay, and submit before next Thursday. Thank you. Okay, we only do the carbon dioxide absorption experiment. Okay. So because this is for the ammonia, this is for the benzene. We not use to this two absorption. We only for the carbon dioxide absorption. Okay, I think that's all for today's course. If you do not have questions, see you later. Um, thank you. Thank you. So bye bye.